Hi everyone. In the previous classes we have discussed about the measurement of temperature, the measurement of pressure, and today in this class we are going to discuss about the measurement of force. So these are the contents today we are going to discuss about. The first one is introduction to the force, which is the definitions of a force, the standards that are involved in the force, and the second topic is methods of measurement of force. Basically there are two methods and we are going to see those two methods for the measurement of force in this class, and various instruments that are used to measure the forces. So the instruments are also classified with respect to the methods of measurement of your force. Different types of instruments, and we are going to discuss about those instruments, their operating principles and their functioning and their figures. All we are going to discuss in this class. So we'll get into the class. The first topic is introduction. So what is force? According to Newton's second law, the force is defined as the product of your mass and acceleration, which we have learned in engineering physics, which is F is equal to ma, which is our Newton's second law of motion. In the Newton's second law of motion, the force is depending upon the mass and also on acceleration. And the units of force is in newtons, and the force is a vector quantity whose unit of measurement is in newtons, and the newton is also equivalent to the force to accelerate a mass of 1 kg at 1 meters per second square. That is, 1 newton is equal to 1 kg into 1 meters per second square. Basically, there are no particular standards for our force. It is depending upon the mass and also on the acceleration. So whatever the standards which we are applying on the mass and the acceleration, those will be reflected on the force also. So it is a well-known fact that the fundamental unit of mass is in kg. Okay, we are going to measure a mass in terms of kg. So although even the acceleration is not a fundamental unit, it is also derived from two other well-defined international accepted fundamental quantities, that is length and time. As we already know, the rate of change of velocity with respect to the time is your acceleration, and the velocity will be the rate of change of your displacement. So the rate of change of displacement will be in length, and with respect to the time means length meters per second is the units of your velocity. Here for the acceleration, it is the rate of change of velocity with respect to the time. That's why meters per second divided by seconds, which is meters per second square. So the acceleration due to gravity, as we already know, we will represent with a letter z, and its value is approximately equal to 9.81 meters per second square. So next is our methods of measurement. There are two methods of measurement of a force. One is your direct method and the second one is indirect method. In the direct method, we will directly compare with a standard one. We will directly compare the unknown force with a known standard force which we have. So that is your direct method. In the indirect method, we will use transducers, maybe an elastic element. If we apply a force on the elastic element, there will be a deflection on the elastic element, which will directly gives us the value of our force. So in case of direct methods, a direct comparison is made between an unknown force and the known gravitational force on a standard mass. For example, we have an unknown force, we have a known force. If we want to measure this unknown force, we will try to compare with the known force. So I measure this unknown force up to such that these known standards and the unknown standards should be equal. For this purpose, a beam balance may be employed. What is this beam balance? And if this is my beam, if I apply a force on this beam, automatically the other end of beam will be moved upwards. If you apply the force, this end of the beam will try to move downwards, the other end of the beam will try to move upwards. So here, if you place an unknown entity, we will try to increase the forces at the unknown side. So where up to such that this beam will be in equilibrium on both the sides. So this is the principle of direct method of measurement of force. In the indirect method, the comparison is made by calibrated transducers that senses the gravitational attraction or weight. The deformation due to the force applied on the elastic member is measured. Here, the transducer elements, that is nothing but the sensing elements which we are using, is it may be a strain gauge, it may be an elastic surface, or it may be a diaphragm, a corrugator diaphragm. All these elements can be used to measure the forces in the indirect method of measurement of forces. So, what are the devices used to measure the forces? So, in this, the first one is scale and balances. In the scale and balances also we have three elements. One is equal arm balance, the second one is unequal arm balance, and the third one is pendulum scale. So all these scale and balance equipments works on the principle of moment, the change in your moments, which we also call them as the direct method of measuring instruments for the forces. So all this equal arm balance, unequal arm balance, and pendulum scale are the direct method of measuring instruments for the force. The second one is your elastic force meter, which we can also call it as a proving ring. And the third one is your load cells, and these load cells were classified with respect to the source, the medium which we are using. If we use the strain gauges, we are calling them as strain gauge load cells. If we use hydraulic fluids, we are calling it as hydraulic load cells. If we use air as a medium, we are calling it as a pneumatic load cell. The first one is scales and balances. In the scales and balances, the first one is equal arm balance. Equal arm, as we already know, equal arm is nothing but if this scales and balances uses a beam. A beam should have equal arms such that at the middle of the beam we are pivoting this beam in the middle. So the length of the beam with respect to this center must be equal on both sides. So an equal arm balance works on the principle of moment comparison. Here we are comparing the moment. Okay, so the beam of the equal arm balance is in equilibrium position. This beam will be in equilibrium position only when the clockwise rotating moment, that is, if we apply the force in the clockwise direction, motion should be equal to the anti-clockwise rotation moment. Motion should be equal to the anti-clockwise rotating moment, that is, m2 L2 is equal to m1 L1, where m1 L1 M1, L1, L2 are our known values for the measurement of force. The only unknown value is our mass, which is M2. So that is unknown force is balanced against the known gravitational force. This unknown force, which is the value M2, is balanced against the known gravitational force. The main parts of equal arm balance is the beam whose center is pivoted, and rests on a fulcrum of a knife edge. So this equal arm balance consists of a beam which is pivoted at the center and rests on a knife edge fulcrum. The either sides of the beam is equal in length with respect to the fulcrum. We will see here. See, this is the beam which is pivoted at the center and it is placed on a knife edge fulcrum, and the distance of the beam with respect to the fulcrum is equal on either sides. That is L1, which is our left side, and L2, which is our right side. Thus, the distance of L1 from the fulcrum is equal to the distance of L2 from the fulcrum. That's why we are calling it as equal arm balance. Equal arm balance. The beam have equal arms on either sides with respect to the fulcrum. And the second one is a pointer is attached. A pointer is attached to the center of the beam. The pointer will point vertically downwards when the beam is in equilibrium. So this is the pointer which is pointing vertically downwards, and this pointer is fixed on the beam at the fulcrum. So at the fulcrum only we are fixing the center of the beam and also the pointer. So we have the provision to place the forces, that is known mass or unknown mass. Okay, so the provision to place masses on either side, either ends of the beam. So these are the provisions which we are placing on either sides of the beam. On one side of the beam we are placing a standard mass, which is our known value. On the other side there will be unknown force, which is which we need to measure. Okay, next, this is the working procedure. Known standard mass M1 is placed at one end of the beam, and unknown mass M2 is placed at its other end. So there will be two masses as usual. One is the standard mass and the other one is unknown mass, which is placed on either sides of the beam. So the equilibrium condition. So in order to make this beam in equilibrium, that means the pointer which we have attached at the fulcrum must and should show the value of 0. That means it has to be exactly in a vertical direction. So then only the beam is said to be in equilibrium. So in order to bring back this beam in equilibrium, the condition is the clockwise rotating moment is equal to the anti-clockwise rotating moment. So this is your clockwise rotating moment, and it must be equal to the anti-clockwise rotating moment. So that is M1 L1 is equal to M2 L2. As the next point is, as the either sides of the beam is equal in length with respect to the fulcrum L1 and L2, the beam will be in equilibrium when M1 is equal to M2. So here it is not at all depending upon the values of L1 and L2. Why? So these values L1 and L2 are fixed. Only the changing element is your masses. In the changing elements of masses also, we are considering one as your standard, which is also fixed. The unknown value, which is of M2, is only the measurand we have to find. So moreover, at a given location, the Earth's attraction will act equally on both the masses M1 and M2, and hence equilibrium condition W1 is equal to W2. So that is, the unknown force or weight will be equal to the known force or the known weight. So the next one is your unequal arm balance. The only difference between the equal arm and the unequal arm balance is, in the first condition we have fixed the values of L1 and L2, but only the changing element is your M2. Okay, here the mass is fixed. The values of L1 and L2 will change here. So this is also works on the principle of moment comparison. So as the name itself says that there will be unequal arms. Here also we are using a beam, but it is not pivoted at the center. It is pivoted apart from the distance from the center. So the working principle is same. Clockwise rotating moment is equal to anti-clockwise rotating moment. So that is F1 F into L2 is equal to Fx into L1. Here L1 and L2 are not equal, and the value of Fx is our unknown entity which we need to measure here. So that is, unknown force is balanced against the known gravitational force. So an unequal arm as usual works on the moment comparison, but it has a graduated beam. The main parts of this unequal arm balance is, the first one is a graduated beam in terms of force pivoted to a knife edge Y. So there will be a beam which is pivoted at a knife edge Y. Let us see in the figure. So this is your beam, this is your beam, a graduated beam on which there will be some graduations which is present on the right side of the beam. So it is pivoted at a knife edge Y, and the distance of the ends of the beam that is on the left side it will have a length L1, on the right side it will have the value L2. So L1 is not equal to L2, and as usual there will be a pointer which is fixed at the fulcrum at the knife edge, which is also pointing vertically downwards, and this pointer will slide over your calibrated scale, and this is your zero null balance pointer. That is, it will the zero represents that the forces are balanced on either sides of the beam. There is another knife edge Z which is placed at the left end of the beam. Why? What is the main provision for this? The knife edge Z will try to avoid the movement of the forces. That is, if the unknown force is more than the mass, automatically it will the value of Fx will be in the downwards direction. If the value of Fx is more, then the mass will try to move downwards. So in order to avoid this mass moving downwards, why this mass will slide over your beam, the graduated beam. So if the unknown force is very low, automatically the mass will try to move downwards. That is, it will come to the end of the beam. So that's why we, in order to avoid those situations, we have kept this knife edge Z. So a leveling pointer is attached to the beam. This is your leveling pointer which is attached to the beam, and a known mass M is attached to the right side of the beam. So to the right side of the beam there is a known mass. So this is your known mass which is attached at the right side of the beam. This creates a known force F. The mass M can slide on the right side of the beam. So this mass will try to slide on the beam. So it will slide on the right side of the beam. So it will not come towards the left side. Why? So there will be some obstruction here. So there is a provision to apply an unknown force Fx by placing an unknown force on the left side of the beam. So here we have given a provision to apply a force, an unknown force in the left side of the beam. Here we will apply the unknown force, and this is our known force. So the right hand side of the beam, which is graduated, is calibrated to get a direct measure of Fx. So whatever the graduations present on the beam, right side of the beam, will have a calibrated scale which is in the form of forces. So for example, if we want to measure the force of unknown force directly, we will try to slide this mass up to an extent such that the pointer will have to come towards the 0. So depending upon the position of the mass on the scale, we will directly predict the amount of force generated on the left side of the beam. So this is the procedure. So this is the operating principle. An unknown force Fx is applied on the left side of the beam through knife edge Z. So here at the knife edge Z, we will apply the unknown force. Now the position of the mass on the right side of the beam is adjusted until the leveling pointer reaches the null balance position. That means will try to move this mass up to an extent such that this pointer will have to show a 0 on your scale. Okay, so when the pointer shows 0, then we can directly predict that the forces on the left side of the beam is equal to the forces on the right side of the beam. So when the leveling pointer is in null position, balance position, the beam is in equilibrium. So that is F into L2 is equal to Fx into L1, where F is the known force on the right side of the beam and L2 is the length on the right side of the beam, where Fx is the force acting, this is the unknown force acting on the right side of the left side of the beam, and the length is L1. So that's why we want to find the value of Fx. That's why F into L1, F by L1 into L2, that is equal to mg, where F is equal to mass into acceleration due to gravity. So divided by L1 and that a whole into L2. So here the mass is the known one, the gravitational a known one, the value of L1 a known one. So the only unknown entity is your L2. So in the equal arm balance, we are going to measure the forces with respect to the change in your masses. So in the unequal arm balance, we are going to measure the forces with the change in the position, that is length L2. So thus the unknown force Fx is proportional to the distance L2 of the mass m from the knife edge y. The right hand side of the beam, which is graduated or which is calibrated to get the direct measure of Fx. So the position of your mass on the right side of the beam will directly gives us the value of your forces in terms of forces only. Okay, so the scale is calibrated in terms of forces. And the third one in our scales and balances is our pendulum scale, which is also known as multi-lever type. So the pendulum scale is also known as multi-lever type, so which is also works on the moment comparison principle. So here the unknown force is converted to torque, which is then balanced by a torque of fixed mass arrangement of a pendulum. So there will be a pendulum here, there will be pendulums here, and we will try to balance these pendulums by applying a force. Okay, so we will try to see. Now let us see the various parts in our pendulum scale. The first one is the scales frame carrying support ribbons which are attached to the sectors. So there are two types of ribbons, and that the first one is your supporting ribbons. So these supporting ribbons which are attached to the sectors. Why we are calling them as supporting ribbons? This is your figure of a pendulum scale. So these are, here is your supporting ribbons. Why? It is supporting the frame on the top. Okay, so there will be a ribbon. One end of the ribbon is attached to the frame, the other end of the ribbon is attached to the sector. So in such a way that the frame, the either sides of the frame is attached with the ribbons to the sectors arranged on either sides of the frame. And the next one, the loading ribbons, the second type of ribbons are attached to the sectors and the load rod. The load rod in turn attached to the weighing platform. The load rod in turn attached to the weighing platform. So this is your weighing platform. So these are your loading ribbons. These are your loading ribbons. So these loading ribbons, one end of the loading ribbon is attached to the top end of the sector. The other end of the loading ribbon is attached to your weighing platform. Okay, so these loading ribbons are also arranged on either sides of your frame. Okay, so there will be an equalizer beam which will connect the centers of your sectors. There will be an equalizer beam. The function of this equalizer beam is to connect the two sectors on either sides of your frame. Okay, to the center of this equalizer beam there will be a rack and pinion mechanism arranged here. Okay, there is a rack and pinion mechanism which is attached at the center of your equalizer beam. So the two sectors are connected on either sides of the equalizer beam. The sectors carry counterweights. So where are these counterweights? Here are the counterweights. So these counterweights are attached to your sector beams. Okay, there are two counterweights arranged on either sides of the your equalizer beam to the sectors. So when we apply the force on your weighing platform, these ribbons will try to move downwards such that this sector will try to rotate in this direction. This sector will try to rotate in this direction. So such that these counterweights will try to lift outwards from the equalizer beam. So in this way it will try to move outwards. Since the pinion, the pointer is attached to the center of the pinion, the rotation of this pinion is directly converts the measurement of your forces on the calibrated scale. Since the pointer is connected to the center of your sector, the rotation of the sector results in the movement of your pointer on the calibrated scale. The movement of your pointer on the calibrated scale. So let us see. The center of the equalizer beam is attached to the rack and pinion arrangement. Rack and pinion arrangement. Here, this is your rack and pinion mechanism. And the pointer is attached to the pinion which sweeps over the weight calibrated scale or your force calibrated scale. Procedure, the unknown force is applied to the load rod. So this is your load rod. Here we will apply the unknown force. Due to this force, the loading tapes, so whatever the ribbons, the loading ribbons are pulled downwards, hence the loading tapes rotates the sector. Okay, so when we apply the force on the weighing platform, since the loading ribbons are attached to your loading platform, so these ribbons will try to move downwards. Since the other end of the loading ribbons are connected to your sectors, so the sectors will try to rotate. The sectors will try to rotate in their respective direction. So as the sectors rotate about the pivots, it moves the counterweights outwards. So these are your counterweights. As soon as the load is applied, the counterweights will try to rotate outwards. The moment increases the counterweight effective moment until the torque produced by the force applied to the load rod, and the moment produced by the counterweights balance each other, thereby establishing an equilibrium. So here, depending upon the moment, depending upon this counterweights, we will directly predict the amount of forces here. Okay, so if the forces, the unknown force is very high, automatically the counterweight will try to move extreme upwards. So during this process of establishing equilibrium, the equalizer beam would be displaced downwards. Why? So when we apply the force here, automatically the pinion, the rack will try to move upwards and the equalizer beam will try to move downwards. Equalizer beam would be displaced downwards. So as the rack is attached to the equalizer beam, the rack is also displaced downwards by the same amount as the equalizer beam rotating the pinion. So what is the amount of rotations of pinion is equal to the amount of displacement of your rack. Okay, so as the pointer is attached to the pinion, the rotation of the pinion makes the pointer to assume a new position on the scale. The scale is calibrated to read the forces directly, and the forces applied on the load rod is directly measured with the help of the pointer on your scale. Okay, so this is about your pendulum scale, and this is about the scale and balances instruments. The next one is our elastic force meter. So this is also known as proving ring. So why we are calling it as a proving ring? There is a ring shaped element on which we are applying a force. So because of the deflections on this ring, we will directly get the amount of force exerted on the ring. So when a steel ring is subjected to a force, when a steel ring is subjected to a force, it may be a tensile force or it may be a compressive force. So ring will have a diameter. Na? So as soon as we apply a force, automatically it will try to deflect. So this deflections is proportional to the applied force when calibrated. So the deflections will directly gives us the value of your force. What are the main parts in the elastic force meter or your proving ring? So the main element or the crucial element in the proving ring is a steel ring, which is of a circular shape, and its cross-sectional view is in rectangular shape. So there are some external bosses attached on either sides of this ring. So there will be some external bosses and there will be internal bosses provided on the outer periphery of your ring. So this is your circular ring, which is made of steel alloy, and the cross section of this circular ring is rectangular in shape. A precision micrometer with one of its ends mounted on a vibrating reed. So a precision micrometer, it is there with one of its ends mounted on a vibrating reed. So here this is the reed which is attached to your internal boss. The other end of the reed is attached to your micrometer wheel. So as soon as when the force is applied, automatically there will be some vibrations on the reed, and these vibrations on the reed will try to rotate this micrometer, and this micrometer will try to displace, and this displacement will directly gives us the amount of force on the scale. The micrometer wheel is turned until the micrometer contact moves forward and makes a noticeable damping of the vibrating reed. Okay, now the micrometer reading is noted, which is the measure of deflection of the ring. So and the device is calibrated to get the measure of force in terms of the deflection of the proving ring. So we will see the experiment that was done on your proving ring. We will try to see the video of the proving ring. So this is the experimental setup of the proving ring here, on which we are going to apply the forces. So initially we will try to take the dimensions of the element which on which we are applying the forces, and this is placed in between the two U-shaped supports. So in this way we will arrange the element, and this is our proving ring equipment. So this is our internal boss, and this is our external bosses. Dial gauge is used to measure the deflections. That is, when the compressive forces is applied on this U-shaped supports, automatically there will be the concrete element which is in between will try to change its shape. So in order to measure that, we have connected a dial gauge here, and this will gives us the amount of force applied on the proving ring. So this is your micrometer, directly converts the forces. Here we have activated the equipment. There are some forces acting. This force is go on increasing the force on your concrete. So this proving ring will try to deform its shape as soon as we apply the forces, and the deflections is also measured at this micrometer or your dial gauge. So as soon as the dial gauge is stopped, automatically there will be no deflections. That means the concrete has broken up. So and that value So the moment at which this dial gauge stops indicating the values, that will be the amount of force generated on the proving ring. At that moment, the amount of forces will be noted. So as soon as this dial gauge stops giving the deflections, it will directly give us the amount of force exerted on the proving ring. Next is our load cell. What is the load cell? A load cell is used to measure the forces, and this is the indirect type of measuring of forces. Here, and the load cells are also classified into three types. In that, the first one is your strain gauge load cell, the second one is your hydraulic load cell, and the third one is your pneumatic load cell. Now, we are going to see what is a strain gauge load cell. Here, the name itself says that we are using the principle of the strain gauges here. So, it will have a cylinder. When a cylinder is subjected to a force, it tends to change in dimension automatically. If we apply a force on any of the object, it will try to change its dimensions. On this cylinder, whatever the cylinder which we are using to apply the forces, we are just bonding the strain gauges. So strain gauges are the metallic conductors. So since we are bonding these strain gauges on the cylinder, whatever the deflections observed on the cylindrical surface will try to give us an electrical voltage from the strain gauge. So on the cylinder, if the strain gauges are bonded, the strain gauge is also stretched or compressed, causing a change in length and diameter. So this cylinder, if we apply a compressive force, automatically its length decreases and diameter increases. So if we apply the tensile forces on the steel cylinder, automatically its diameter decreases and its length increases. So this change in dimension of the strain gauge causes its resistance to change. But the strain gauge resistance will change, and this change in resistance results in the measure of our applied force. This change in the resistance is directly proportional to the applied force. So that we will get the output as in the terms of voltage. So what are the main parts involved in the strain gauge load cell? So as usual, we have discussed a cylinder made of steel on which 4 identical strain gauges are mounted. So here we are using 4 strain gauges, and we are bonding these 4 strain gauges on the surface of the cylinder. Okay, so on this strain gauges were bonded in such a way that R1 and R4 will try to measure the linear motions of the cylinder, and R2 and R3 will try to measure the lateral dimensions of the cylinder. So R1 and R4 measure the longitudinal dimensions, whereas R3 and R4 R3 and R2 will try to measure the lateral dimensions of the cylinder. So if we apply a force on the cylinder, automatically these strain gauges will absorb the there will be a chance in the change in the resistance of these strain gauges. Since we have connected these 4 strain gauges to in a Wheatstone bridge, automatically there will be some output voltage. So we will discuss it clearly. So out of 4 strain gauges, 2 of them, that is R1 and R2, are mounted along the direction of the applied force. R1 and R4 are arranged along the direction of your applied force, whereas and R3 and R4, R2 and R3 are mounted circumferentially at right angles to the R1 and R4. So here 2 strain gauges which are placed in a opposite to the cylinder. One is placed at one side of the cylinder and the other one is placed at the other side of the cylinder. Next, R2 and R3 were perpendicular to this R1 and R4. So these are placed like this. Okay, the other two strain gauges R2 and R3 are mounted circumferentially at right angles to the previous ones, that is R1 and R4. So here is your R1 and R4. These are R1 and R4, which are placed at right angles to the R2 and R3. The four gauges are connected to the four limbs of the Wheatstone bridge. So we are using the four strain gauges and we are connecting these four strain gauges to a Wheatstone bridge. So there will be a potential difference observed at the terminals N and P. This potential difference will result in the change in the voltage in the galvanometer, which is provided in the here. So let us see the description. When there is no load on the steel, all the four gauges will have the same resistance. For example, at the initial conditions, we are not at all applying any force on the steel cylinder. Since we are not applying any of the forces on the steel cylinder, there will be no change in the resistance of your strain gauges. That means the galvanometer, which is placed in between the terminals N and P, will show 0. So as the terminals N and P are at same potential, the Wheatstone bridge is balanced and the output voltage will be 0. Now we are applying the force. So how much we are applying the force, that we need to measure. So it may be a compressive force or it may be a tensile force, any of the one. So if we apply any of the force on this steel cylinder, automatically this vertical gauges R1 and R4, there will be the change in the resistances. So which will undergo, if you say for example, if we are using a compressive force, this compressive force will change, will be in the along the axis of your cylinder. So along the axis of the cylinder, we have provided the resistors R1, strain gauges R1 and R4, which will undergo compression, and there will be decrease in the resistances. Okay, so when there will be compression, there will be decrease in resistance. When there will be tensile, there will be increase in the resistances. So at the same time, the horizontal gauges, that is R2 and R3, which are placed exactly in perpendicular to R1 and R4, will also undergo tension. There will be increase in the resistances. Thus, when strained, the resistance of the various gauges changes. So as soon as if we apply the strains, the resistance also will change. Now the terminals N and P will be at a different potential, and the change in the output voltage due to the applied load becomes a measure of your force. So whatever the output voltage which we are getting, because of the potential difference between the points, junctions N and P, so that value, that deflections, that potential difference will result the amount of force which we are applying on the steel cylindrical body. So there are some conditions. The strain gauge load cells are used when the load is not steady. So the strain gauge load cells are used in the vehicle weigh bridges and tool force dynamometers. So if you want to measure the tool force with the help of a dynamometers, we are using this strain gauge load cells to measure the amount of forces generated. Okay, so this is about your strain gauge load cell. Now we are going to discuss about hydraulic load cell. What is this hydraulic load cell? The name itself says that it utilizes the hydraulic fluids. That means when a force is applied on the liquid medium, so there will be a container on which a liquid medium is present. If we apply the force on this liquid medium, automatically the pressure on the liquid is also increases as usual. So if we apply the force, automatically its pressure will be increased. This increase in pressure of the liquid is proportional to the applied force. So the amount of force which we apply is directly proportional to the increase in pressure. Hence, the measure of increase in pressure of the liquid becomes the measure of applied force when calibrated. So as we go on increasing the pressure, this change in pressure will directly result the change in your force. So here whatever the equipment which we are using to measure the pressure will have the calibrated scale in terms of the forces only. So we are the scale will have the values in terms of the forces itself. So what are the main parts in the hydraulic load cell? One is a diaphragm, a piston with a loading platform placed on the top of a diaphragm. So here this is the chamber, lower chamber, on in which we have placed a liquid or oil in the lower chamber. So the upper chamber is used to support the diaphragm, that is, it is used to lock the diaphragm in between the piston and the lower chamber. So this upper chamber and the lower chamber were sealed by placing a diaphragm in between this lower and the upper chamber. Okay, so these lower and upper chamber are sealed with the help of studs. Okay, so on the top of this diaphragm we have placed a piston. On the top of this piston we have given a provision or a platform on which we are going to apply the forces. Okay, so this is your packing seal. So this is used to avoid the leakages of the oil into the upper chamber. So this is your packing seal. So this is the way or the passage of the liquid that will pass towards the pressure gauge. So a liquid medium which is under preloaded pressure is on the other side of the diaphragm. So a liquid medium which is under the preloaded pressure is on the other side of the diaphragm. That means on one side of the diaphragm there will be a piston. To the other side of the diaphragm there will be a liquid medium. Okay, so a pressure gauge connected to the liquid medium. So generally we will use Bourdon tube type of pressure gauge, and this Bourdon tube type of pressure gauge is connected to your liquid medium to measure your forces. Okay, so as soon as we apply the forces on the platform which is placed on the top of this piston, these forces will try to move this piston towards and downwards. Since the diaphragm is placed under the piston, this diaphragm will also try to deform towards the downwards, which results on exerting the pressure on the liquid. So the pressure that is exerted on the liquid will directly results in the deflection of your pointer on your pressure gauge. Okay, so this pressure gauge, the scale is calibrated in terms of your applied forces only. So this is the procedure. As we have already discussed, the force to be measured is applied to the piston. So we will apply the force on the piston. This applied force moves the piston downwards. This applied force moves the piston downwards and deflects the diaphragm, and this deflection of the diaphragm increases the pressure on the liquid medium. So as soon as we apply the force on the piston, this piston will try to deform this diaphragm. This diaphragm will be deformed, so resulting in exerting the pressure on the liquid medium. Since we are exerting the pressure on the liquid medium, automatically there will be deflections observed on your pressure gauge. So the increase in pressure of the liquid medium is proportional to the applied force. So the increase in pressure is measured by the pressure gauge which is connected to your liquid medium. So the pressure is calibrated in force units. That means the scale of your pressure gauge is calibrated in force units itself, and hence the indicating in the pressure gauge becomes the measure of your force applied on the piston. So which we will get the forces as our output by placing an input on the piston. So these are the conditions. As the note 1 is, as the hydraulic load cell is sensitive to the pressure changes, hydraulic load cell is sensitive to pressure changes, the load cell should be adjusted to zero setting. The load cell should be adjusted to zero setting. before using it to measure. So at initial conditions, before applying the forces, the pressure gauge must be in the zero position. The load cells have an accuracy of the order 0.1% of percentage of its scale, and can measure the loads up to 2.5 into 10 to the power of 5 kg forces. Okay, so it has the ability to measure up to the loads of 2.5 into the 10 to the power of 5 kg forces, and the resolution is about 0.02%. And here we are going to discuss about pneumatic load cell. In the pneumatic load cell, we are just changing the liquid, and we are just replacing the air in the place of liquids. So if the force is applied on one side of the diaphragm as usual, and the air pressure is applied on the other side, so some particular value of the pressure will be necessary to exactly balance the forces. So this force, which air pressure which we are applying to in the opposite direction of the applied force, will try to balance this position. So this pressure is proportional to your applied forces. Whatever the pressure is applied by the pressure which we are creating with the help of our air is proportional to the applied force. What are the main parts here? So here also we are using a diaphragm. So the diaphragm of type corrugated diaphragm. Why we are calling it as a corrugated diaphragm? Why? Because it has like this bulges. So this profile. So if a diaphragm has this profile, we call it as a corrugated diaphragm. So if it has a flat surface, then we call it as a flat diaphragm. So a corrugated diaphragm with its top surface attached with the arrangement to apply the force. So on the top of the diaphragm, there is we have placed a boss on which we are going to apply the forces. So an air supply regulator, nozzle, and a pressure gauge are arranged. Here there will be air supply regulator, here is a nozzle, and here is our pressure gauge. Okay, so next a flapper is arranged above the nozzle. So what is this flapper? This is the flapper which will try to open and close the nozzle, opening of the nozzle. So this flapper is arranged on the top of the nozzle, and it is connected to your applied force. So now we are going to discuss the operating procedure. How the force is to be measured is applied on the top side of the diaphragm. So on the top side of the diaphragm, here we will apply the force, which will result in the deflection of your corrugated diaphragm. So this diaphragm will try to move downwards such that this flapper box will close the nozzle opening. So due to this force, the diaphragm deflects and causes the flapper box to shut off the nozzle opening. Now an air supply is provided at the bottom of the diaphragm. So from the bottom of the diaphragm, we will try to give the air supply. So we will supply the air in such a way that we have to make this force to move upwards. Such that, so here the important element is the regulator. So if we change the position of the regulator, automatically the air supply pressure will be increased. So this pressure will be now air bottom of the diaphragm. As the flapper closes the nozzle opening, the back pressure results underneath the diaphragm. So here, since it was closed here, since we have closed here, the air will try to move towards this side, and it will try to move this side also. Okay, since the flapper is closed here, the pressure will be in the backward direction. That means it will be in the opposite direction underneath the diaphragm. This back pressure acts as a diaphragm, producing an upward force. So here, since we are obstructing the passage of the air through the nozzle, so there will be some back pressure, and this back pressure will try to move this diaphragm towards upward. That means by the application of this force, the diaphragm will try to move downwards. Since we are applying the air pressure from the opposite side of the diaphragm, so this diaphragm will try to move upwards. So air pressure is regulated until the diaphragm resolves to the preloaded position. So the initial position. So how do you know the preloaded position? Automatically, the position at which the air will comes through this flapper. Okay, so this is the flapper now. So this flapper will there will be some opening here. So we will try to increase or regulate this air pressure in such a way that a little bit amount of air force will try to come through this nozzle opening. So the nozzle will open only when the applied force is equal to the air pressure which we are giving from the bottom of the diaphragm. So at this stage, the corresponding pressure indicated by the pressure gauge becomes the measure of your applied force when calibrated, and the output pressure will be in terms of the force, applied force, which we have found. So there, this also have two notes. Note 1 is the pneumatic load cell can measure loads up to 2.5 into 10 to the power of 3 kgf as usual in your hydraulic load cell, and the accuracy of this system is 0.5% of the full scale. So the class about the measurement of forces. If you have any doubts, kindly give a comment below. Thank you.